Ulas from Krakow, who speaks on solutions of certain meta Fibonacci recurrences.
Thank you very much. Thank you very much for this introduction. Yes, and I will speak about my recent findings of concerning the solutions of certain meta Fibonacci recurrences and this talk is based on the joint work with Bartosz Sobolewski. Okay, so let us start with some introduction and motivation. I believe that everyone here knows what a Fibonacci sequence is. This is just f0 equal to 0, f1 equal to 1, and then we define fn as the sum of two previous terms. And there is many applications of this famous sequence and many various and many generalizations of this sequence. And it seems that many of these generalizations can be seen as a subclasses of the class of so-called meta Fibonacci sequences. And here I say that a sequence is a meta Fibonacci sequence if it is a solution of the recurrence equation of the following form, where P and Q are some expressions involving n, fn minus 1 up to fn minus k for some k. And in fact, to get a sequence, we need to specify initial conditions f1, fi, where of course I depends on this P and Q. So this is quite a general definition. And of course, for some initial conditions, the corresponding sequence may be not well defined. For example, if for some n we have Pn less than or equal to 0 or Qn less than 0, then the term with index n cannot be computed. And we say then that the sequence dies. Okay, so a typical example of meta Fibonacci sequence is the following. We can take Pn equal to n minus fn minus 1 and Qn equal to n minus fn minus 2. So if you take initial conditions f1 equal to 2 and f2 equal to 1, then we can compute f3 is equal to 3, f4 is equal to 5. But if we try to compute 5 minus f4, we get 0. So because we don't know what is f0, we do not define this value, we cannot compute the value of f5. So yeah, sometimes we have a problem with definition of this meta Fibonacci sequence. And this class of meta Fibonacci sequence is quite broad. And of course, contains Fibonacci sequence, for example, the sequence of powers of 2, and many other interesting and quite exotic sequences. And one of the most famous probably example is the Hofstadter sequence, which is defined in the following way. We defined Q1 equal to Q2 equal to 1. And for n greater or equal to 2, we define this in the following way. So look, that is very similar to this previous example where we have f1 equal to 2. Here we have f1 equal to 1. And what is really interesting, we don't even know whether this sequence is well defined. So whether it will die or not for some n, but we know certainly that it lives for n less than 10 up to 10. Okay, so there are many different variants of the Hofstadter sequence, and some variants are easy to understand. And one of the examples is the sequence introduced by Tane. So this sequence starts with the following. We have T0 equal to T1 equal to T2 equal to 1. And here is a definition of the recurrence. And one can prove that this sequence is well defined. So we can compute the Tn for each n. And in fact, each positive integer appears as a value of T. Okay, but browsing through the literature concerning meta Fibonacci recurrences of various kinds, we observe that in each case, the expression P and Q used in the definition of the recurrence one. So let's just recall this definition here. Contains besides n, contains at last one term of the form fn minus k for some k. So moreover, in each known case, there is an integer, positive integer a, such that for each b belonging to the set 0 up to a minus 1, the sequence f along the arithmetic progression a times n plus b is bounded from above by a linear function in R, or is governed by a specific linear recurrence sequence with eventually exponential growth. So these two observations motivated us to ask the following question. So consider this recurrence. So here we have typical term n minus f n minus u plus something which is really similar to Fibonacci sequence and fix u and phi. So the question is, what can be said about the sequence solving these recurrences for various sets of initial conditions, and whether we can expect that the existence of solutions which are not simultaneous solutions of linear recurrent sequences, neither are slow growing or unpredictable or chaotic like in Hofstadter sequence. Of course, there is a problem with definition, because for most choices of the initial conditions, this sequence will die. So to solve these questions, so the case u equal to v x equal to 1 is very easy, and in fact one can prove that you have an explicit solution which is linear, so it's not really interesting. So something non-trivial starts to be in the case where u is equal to 1 and v is equal to 2. So yes, so in order to avoid the problem with dying sequences, we assume that the value of the sequence is equal to a, which is fixed, for n less than equal to 0. So the problem with dying sequence is eliminated, and we consider this sequence HAB, which is defined in the following way. So we have A for n less than equal to 0, B for n equal to 1, and this recurrence holds for n greater than 1. So A and B, we assume that A and B are positive integers. Okay, so we start our analysis with the sequence H11. So in order to simplify the notation, we just write Hn is equal to H11. And here are the first 26 values, 26 terms of the sequence H. So 1, 1, 2, 2, 4, 3, 6, 4, 10, 5, and so on. But so we can observe that we have in this sequence, there are strings quite similar to the natural numbers, 1, 2, 3, 4, 5, 6, 7, and this is not an accident. And before we prove that, we need to recall the Pruett-2-Morse sequence, which will be called the Ptm sequence for short in the sequel, which is defined by the following recurrence: T0 equal to 1, and T2 times n is equal to Tn, and T2 times n plus 1 is equal minus Tn. So this is essentially the same sequence as the one mentioned by Bartosz in the previous talk, but is defined on the alphabet containing -1 and 1. Okay, so first result is the following, that we have H2 times n is greater or equal to 2 times n, and that the values of along the 2 times n plus 1 is equal to n plus 1. Moreover, this Pruett-2-Morse sequence is useful here, and we can prove this interesting identity. So The proof is easy. Essentially, this is induction by K and N. And as a consequence of this result, we can prove that this sequence is not too easy, in the sense that the H2 times N is not a polynomial for all N greater, for all N a positive natural numbers. So there is no polynomial of this type, but still the question whether is a quasi-polynomial or something like that. This is natural. And yeah, so as a consequence of the theorem 1, we can also get a recurrence, which is in some sense eliminate the needing of the computing the nested terms. It is not very convenient, but is the step in the right direction, I believe. But in fact, all this can be simplified, and we have this theorem 4, which essentially says that H2 times N plus 1 is equal to N plus 1, and H2 times N is just the sum of the values of Hi for I equal to 0 up to N. So this simplifies things a lot, and we have very nice application of this result. You can simplify the recurrence one more time, and this is the simplest, I believe, this is the simplest recurrence which can be proved in this for this sequence. So we have H0 equal to H1 equal to 1, and here for N greater or equal to 1, we have two recurrence relations for the values odd and even. So having the recurrence of this type is quite natural to compute the generating function. So let capital Hx be a ordinary generating function for our sequence Hn, starting from n equal to 0 up to infinity. And then one can prove that this particular function satisfy the Mahler type functional equation. So this equation, this functional equation, is quite easy to prove using these recurrence relations for H. And okay, having this, we can prove much more. And as an application of this theorem, we can prove that the generating function Hx is of the sequence H is transcendental over Qx. So in particular, this means that the sequence Hn is quite complicated. So in particular, it's not an algebraic function. So in particular, not a rational function. So do not satisfy linear recurrence sequence with constant coefficients, nor is the sum of such sequences. Okay, so sketch of the proof. We can treat this H as an element of the field of formal power series defined over C, and we can use the Nishioka theorem, which says that if we have a formal power series which satisfies functional equation of this type, where D is fixed positive integer greater or equal to 2, and the phi is a rational function in two variables x and y, then F is rational or transcendental. So in our case, D is equal to 2, and our phi is given here. So in fact, we need to prove that this function is not rational. If it will be not rational, then we will have from the Nishioka theorem that it is transcendental. So to prove the non-rationality of the series H, we compute its remainder modulo 2. So we compute the series Gx, which is defined over Z2 in the field of the formal power series with coefficients in Z2, and from the functional equations, so we can compute modulo 2 this equation. So then this square will get out, and we get these polynomial solutions for G. So this is equation of degree, polynomial equation of degree 2, and one can check that this polynomial is irreducible in the ring of the polynomials x in two variables x, y over Z2. So this means that G is not rational even as a series here. So this particular implies that Hx cannot be rational in this field here. So applying Nishioka theorem, we get that this generating function is transcendental over Q of X. So using this theorem, we can especially in particular prove that the sequence H grows exponentially fast. But how we can do that? This is a bit more difficult. So first we need to recall the generating function of the Ptm sequence. This is the generating function for the sequence. It particularly satisfies this functional equation. We can also define Bx, which is 1 over Tx, and this is the famous function which counts the number of binary partitions of n, or in other words, partitions with parts in the set 2 powers of 2 for I in natural numbers. And from these functional equations, we can deduce these particular functional equations, and we have nice recurrence relations satisfied by this sequence bin n. And okay, so to get the result, we can iterate the functional equations for H, and for each k, we can check that Hx is given by this formula. So let us note that here we have H in x up to 2 up to k. So taking the limit k, going with k to the infinity, one can we get the identity that our function h is equal to the sum given here, where h dash is equal here. So which is here we should have b x squared, and this hi is given here. So here the end coefficients in this power series expansion is equal to 0 if n is odd, and is just equal to number of binary partitions of n over 2 if the number n is even. So moreover, we can understand the coefficients of each term here, because Cin is equal to number of partitions of the number n minus 2 up to I minus 1 into elements of the set 2 up to I. And the last element 2 up to I can take 2 colors. So we can write this identity. And finally, where here we have expression for the dn, we have the identity that h2 times n is equal to bin n plus d2 times n. So this thing is greater or equal to 0. These things grows exponentially fast, which is proved by De Bruijn, and we get the result. Okay, so what is going on in the case where b is greater or equal to 2? And essentially, very similar arguments allow to prove that we have recurrence like given here. Then we have an generating function of the similar type, which is Mahler type functional equation. So again, we can compute some expansions, and especially prove that this function is still transcendental over Qx. And what is interesting that in fact you can give a precise result which gives that the value of the H1b up to 2 times n plus 1 is the linear combinations of the binary partition functions and the H11. So this is quite interesting observation, I believe. And so we can quite good, and we have a quite good understanding of this sequence for the pair A equal to 1 and B greater or equal to 2. So what is really nice, in case where A is greater or equal to 2, we can just easily compute the solutions which in terms of the linear functions given here. So for example, if 2A is greater or equal to 2 and B is greater or equal to 2, then we have these simple expressions for the solutions, similarly for the case B equal to 1. And the last case is the pair A equal to 2 and B equal to 1. And again, we get something really, really simple. So some final remarks. It is quite natural to investigate further this question. The question whether we can expect some new phenomena in the case where U and V are greater or equal to 2, both are greater or equal to 2, and whether there are connections from partitions functions. Yeah, so we said that the case U and equal to V and equal to 1 is easy. We present the results concerning the case U equal to 1 and V equal to 2. And what is interesting that if we take U equal to 2 and V equal to 1, then again we get simple characterizations of the solutions. So the first really non-trivial result is the case when at last one U or V is greater or equal to 3. But I believe that even more interesting question is the following. So how close the meta Fibonacci sequences are similar to linear recurrence sequences. They are not too similar, but the question is the following. So we have a sequence which is Z-line linear combinations of meta Fibonacci sequences, and the values of the sequence are positive natural numbers. So, and the question is whether F itself is a meta Fibonacci sequence. So this is quite natural questions, I believe, and this in particular would imply that the binary partitions function, which counts the partitions into powers of 2, would be a meta Fibonacci sequence. It's not clear for me whether this is true or not. And so this is more specific presented in the question whether this sequence can be realized as a subsequence of a meta Fibonacci sequence along an arithmetic progressions. Of course, we can go further and ask whether we get something new if we add the one more value F2 equal to C, and we ask whether we obtain some new interesting sequences. Okay, thank you very much.
Thank you very much for a very nice talk. Do we have any questions for our speaker? If not, then I thank you once again. And
thank you.
We have a break now for breakfast, lunch, or dinner, depending on what time zone you are in.